So I did Unit 8 Acids and Bases. And so, first of all, you need to know what an acid and a base is. So the Arrhenius definition is an acid is a substance that will increase the amount of hydrogen ions in the solution, and a base is something that will increase the concentration of OH ions in the solution. And the Bronsted-Lowry definition is an acid is a proton donor and the base is a proton acceptor. Um, for example, if you're taking a look at the reaction I have up here, sulfuric acid plus water, sulfuric acid is giving a hydrogen to the water molecule and losing one. So its products are HSO4 minus plus H3O plus. So in this case, the sulfuric acid would be the acid, the water would be the base, and the HSO4 would be the conjugate base, and the hydronium ion will be the conjugate acid. And an important thing to remember is that the stronger an acid or base is, the weaker its conjugate will be, and the weaker an acid or base is, the stronger its conjugate will be. And then the thing on the right is the auto-ionization of water. It's basically water reacting with itself to form hydroxide and hydronium ions, and the equilibrium constant for this at 25 Celsius is 1 times 10 to the power of negative 14. So that basically means the concentration of the hydronium concentration of hydronium times the concentration of hydroxide equals that constant I have right there. And then we ignore water because it's liquid. A trend that you should remember: as temperature increases, your Kw will also increase. So strong acids and bases are assumed to dissociate 100%, so the K value will be very, very large. Because of this, the initial concentration of the acid or base will be equivalent to the stoichiometric amount of H3O or OH in the system after reaction is finished. So this is an example multiple choice question they might give you. So we know that barium hydroxide is a strong base, so it's not going to react. So it's going to react completely with the water. We need to find the initial concentration of barium hydroxide, and we can determine the concentration of the OH ions to find the pOH. After that, we subtract it from 14 to find the pH. Since barium hydroxide dissociates into 2 hydroxide ions, the final concentration should be multiplied by 2 before finding the pOH. And so another good thing to remember is the format for the ICE table. It's basically, its purpose is to simply see how the concentrations of the products and the reactants are changing. In acid-base reactions involving water, you can ignore water because it's a liquid and we don't care about it. And so ICE tables are generally used to find an unknown concentration of the products or reactants, or the equilibrium constant. So Ka and Kb are known as the acid and base dissociation constants. It's the products over the reactants, like every other K value. And yeah, again, it excludes water because weak acids and bases do not dissociate completely. We got to use Ka or Kb values to find the concentration and the pH. Percent ionization is just calculating how much of the acid or base has dissociated into ions. The equation is the concentration of hydrogen or hydroxide at equilibrium over the concentration of your acid at the beginning. A trend worth remembering is that the percent ionization will increase as you dilute the solution when it is in equilibrium. So there's a couple of key points of a titration curve that you should know how to find. The most important is probably the equivalence point. That's when the analyte has reacted completely with the titrant. For strong acids and bases, the pH at the equivalence point is 7, but for weak acids, but for reactions with including weak acids or weak bases, you're going to have to do a little more work because the conjugate of the weak substance is going to react with the water again. Because remember, conjugates of weak substances are strong, and so you can't ignore them. And the pH of the initial point is easy to solve. You can use an ice table to find the concentration of your ions using the equilibrium constant. And the half equivalence point is when your pH equals your pKa. It's also when the half of the reaction takes place, hence why it's called the half equivalence point. And to find an unknown concentration or volume for titration, we use the equation M1V1 equals M2V2, where M stands for molarity and V stands for volume. So the molecular structure of acids and bases. The weaker the bond that is holding the hydrogen atom, the weaker it is, the stronger the acid will be because the hydrogen has an easier tendency to pop off. The more oxygens in an acid, the stronger the acid will be because oxygen is more electronegative and it's attracting the electrons to itself, making the whole molecule more polar, and it will let the hydrogens pop off easier. And here's a list of all the strong acids. Here's just a list of the strong acids and strong bases. There's more strong bases, but those 6 strong acids are all that we need to know for AP. And we can assume that they will dissociate 100%. The strong bases are often the group 1 or 2 elements paired with hydroxide. So you'll need to know the relationship between pKa and pH. You should know that if the pH is less than the pKa, the acid is more prevalent in the solution. If the pH is greater, then you have more conjugate base in the solution. Last thing is buffers, and they're basically just a weak conjugate acid-base pair that have similar concentrations to each other. When you add a little bit of acid, the base will react with it, and if you add a base, the acid will react with it, and basically it neutralizes it, and the pH doesn't change very much. A buffer is something that resists pH change. The best type of buffer is one where you have equal amounts of acid or base and its conjugate. And so here's the Henderson-Hasselbalch equation, a very important equation, and it's used for finding the pH of a solution given the pKa and the concentrations of your acid-base conjugate pair. So here are the formulas that you'll have to know. M1V1 equals M2V2. You use that one when you're doing a titration usually, and if one variable is unknown, for example, you knew the volume of the first one and the molarity and volume of the second one, and you're trying to find the molarity of the first one. The pH plus pOH equals 14. This comes from the autoionization of water equation, the pKw, and this only applies at 25 Celsius. pH equals pKa plus log of A over your conjugate base over your acid. That's the Henderson-Hasselbalch equation. And the last one is your percent ionization equation. And here are the units. So sample FRQ number 1. So let's see, propanoic acid is a carboxylic acid that reacts with water according to the equation above. At 25 Celsius, the pH of a 50 milliliter sample is 0.2 molar propanoic acid is 2.79. And the first question is asking you to identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Okay, so we know that propanoic acid is losing the hydrogen in this case, and it's giving it to the water. So that means that the propanoic acid is the acid, the water is the base. Clearly label which is the acid and which is the base. So it's only asking for one pair, so we can say propanoic acid is the acid, and then its conjugate is CH3, CH2, COO minus. So those two. And then it's asking you to determine the Ka for propanoic acid at 25 degrees Celsius. So you would set up an ice table for this. You don't need to, but it helps to just see it. So you have 0. I'm going to open up Photoshop for this. So I'm going to draw an ice table. So initially you're at, you have 0.2 molar propanoic acid. So we put that here. That's your initial for the reactant. We ignore H2O, and we have your conjugate base and your conjugate acid. So those are both 0. And then what happens is that this reacts. So we're going to be subtracting something here, and this is going to be gaining. So, but how much are we subtracting? How much are we gaining? We're trying to find. We can find that using this pH right here, 2.79. If we do 10 to the negative 2.79, we can find the concentration of the hydrogen atoms in the solution. So I got that it was 0.00162. Yep. And so you subtract that, you get 0.198, 0.0162, and it stays the same for that. And so the Ka will be your products over your reactants. So it's going to be 0.0162 squared over 0.19198. And that equals approximately 1.325 times 10 to the negative fifth. And that's what I got. And then for each of the following statements, determine whether the statement is true or false. In each case, explain the reasoning that supports your answer. So the pH of the solution prepared by mixing the 50 milliliter sample with a 15 milliliter sample of 0.2 molar NaOH is 7. Okay, so we know that's false because propanoic acid is a weak acid. That means at the equivalence point, its conjugate base is going to react with the water to form more OH. It's going to take the H from the water, leaving more hydroxide molecules in the solution, and it's going to increase the pH. So um, the pH at the equivalence point is going to be slightly above 7. If the pH of the hydrochloric acid solution is the same as the pH for the propanoic acid solution, then the molar concentration of the hydrochloric acid solution must be less than the molar concentration of the propanoic acid solution. This is true because hydrochloric acid dissociates completely. It's a strong acid, so its molarity is going to have to be smaller if the pHs are going to want to be equal. So sample FRQ number 2. Hypobromous acid is a weak acid that dissociates in water as represented by the equation above. Calculate the concentration of H plus in an HOBr solution that has a pH of 4.95. So that's really easy. You just do 10 to the negative 4.95, and then that gives you, what does that give you? That gives you 10 to the negative 4.95, 1.12 times 10 to the negative fifth, and that's the concentration of H plus ions. B, write the equilibrium constant expression for the ionization of HOBr in water, then calculate the concentration of HOBr in an HOBr solution that has H plus equal to 1.8 times 10 to the negative fifth molar. Okay, so we need to use the concentration of the H plus ions. If H plus is 1.8 times 10 to the negative fifth, that means OBR minus is going to be the same as well, so we're going to square that. And that's over your concentration of your HOBr. So we'll put that as X, and our Ka is given, so it's 2.3 times 10 to the negative 9. And so all we do is just find for X, and I got X is equal to 0.14 molar. So yeah, a solution of BaOH2 is titrated into a solution of HOBr. Calculate the volume of blah blah blah. It's just an M1V1 equals M2V2 equation. We're trying to find the volume of barium hydroxide. So we set that equal, and then we get that the volume is 82.5 milliliters. And then second part, indicate whether the pH at the equivalence point is less than, equal to, or greater than 7. Okay, so another one of these questions. It's going to be greater than, because again, HOBr is a weak acid, and so its conjugate base is going to react with water, forming more hydroxide ions. Calculate the number of moles of NaOBr solid that will have to be added to 125 milliliters of 0.16 molar HOBr to produce a buffer solution with um, concentration of hydrogen of 5 times 10 to the negative 9 molar. Okay, so this one you gotta use the Henderson-Hasselbalch equation. Um, it's given, we're given the concentration of hydrogen, so we can find the pH. Clear this up a little bit. So we do the 10 to the negative 10 to the negative of this number, 5 times 10 to the negative 9, and then we get 8.3 equals your pKa. So negative log of this right here, 2.3 times 10 to the negative 9. That gives you 8.64 plus log your conjugate over your concentration of your acid. And we found out that it's 0.16 molar. So you solve for A. So if you move that over, it becomes negative 0.34 equals log of A over 0.16. And then you do some more simplifying, and then you get that A will equal 0.0736 molar. But you're not done because the question is asking you for the number of moles. So they told you that you had 125 milliliters, so this equals x over 0.125 converted to liters. Multiply that over, you get x will equal 0.0092. So that was a pretty tricky one. HOBr is a weaker acid than HBrO3. Account for this fact in terms of molecular structure. So this was exactly what we were talking about before. HOBr has two less oxygens than HBrO3. This means HBrO3 has two more oxygens that have more electronegativity, and the electrons are making the whole entire molecule more polarized. So that means that H is going to be able to pop off easier for HBrO3. The more oxygens it has, the stronger acid it is. And so that took a pretty long time, but yeah, we're done. Thank you.